Okay, today is the big day, 2.5. It all comes to a head today. Zeros and polynomial functions. But here's the thing, we've done nothing but talk about zeros and polynomial functions. So what's new today is that they're just throwing us out there. They've been hinting at us what the zeros are so we can find them. And now we're out there on our own having to find all the zeros. Okay, so let's try it. There are a couple of theorems that we use to help us find these zeros. And so one of them is called the fundamental theorem of algebra. We kind of have already hinted around at this, but here it is officially. If f of x is a polynomial function of degree n, so if it's like the highest power is a third degree, or the highest power is a sixth degree, whatever it is, then there are n complex zeros. So if it's a sixth degree, there's going to be 6 zeros. If it's a third degree, there's going to be 3 zeros. However, and so we kind of sort of already knew that. But notice it does say complex zeros, so those might be real or they might be imaginary. That's what's kind of new for us today. The other theorem that helps us find the zeros is called the rational zero theorem. And it says that if you have a polynomial function, then all of its rational zeros, so not all of them, but the rational zeros, have the form of p over q, where p is going to be a factor of your constant, q is a factor of your leading coefficient. All right, so that seems kind of like a mouthful. I'm not sure. Let's go ahead and look at what that means. This is the kind of thing that we're dealing with. They're going to give us this polynomial function. All right. But in the past, they kind of have told us like what one of the zeros was or something so we could get started on this problem. But what I have here is a fourth degree polynomial. So what that tells me is that my fundamental theorem of algebra says that whatever degree it is tells me how many zeros I'm going to have. So I'm going to have 4 complex zeros on this problem because it's a fourth degree. All right, the rational zero theorem, that was the mouthful earlier. Okay, let me just stop for a second and say you really, really need to take notes as we go, and it would be best if you had your note sheet because I'm going to keep referencing previous problems, and so you'll need to be able to look back at those problems. So make sure you're taking notes as we go. All right, so on this one, the rational zero theorem, looking back at that previous slide, it says that all of your rational zeros will have the form of p. P is a factor of your constant. So my constant is a 6, or really a negative 6. And so my factors of 6 are 1, 2, 3, and 6 over q. And q says that it is the factor of the leading coefficient. Well, my leading coefficient is up here, and it's just a 1. So that makes it easy. Factors of 1 are just 1. And these can all either be positives or negatives, and so we put a little plus or minus to show that. So really I have 8 options here for my rational zeros. It could be a 1, a 2, a 3, or a 6. And all I'm doing is like looking at that right there, saying, oh, okay, 6 over 1 is 6, or 3 over 1 is 3. Now, I'm only going to have 4 of them. I have 8 to choose from to get my rationals. But remember also that they don't necessarily have to be rational. They might be imaginary. And so this is just kind of my starting point. All right, so once I've used the fundamental theorem of algebra, and I do my rational zeros theorem to get a starting point, I'm going to go back to that remainder theorem. And so let's refresh our memory on the remainder theorem. Remember that it says that if you do f of whatever your k value is. In this case, and I'm going to keep my life simple, I got 8 of them to choose from over here. I'm going to start with the easy ones. I'm going to put in 1. So if I find f of 1, so that means plug 1 into my function, whatever I get back is my remainder. So plug 1 in. 1 to the 4th is 1, minus 1 to the 3rd, plus 1 squared, minus 3 minus 6. Okay, all I'm doing is plugging 1 into my polynomial function. All right, and then we're looking at what does that end up equaling. All right, looks like the positive 1 and the negative 1 would cancel. I get a 1. Usually what I do is I combine my negative numbers, so that's a -9 and a +1, so that's a -8. Okay, so if I plug 1 in, I get -8 as a remainder. Okay, what that really means to me is that 1 is not going to be one of my zeros because I got a remainder. If I don't get a remainder, that's a good sign. So I know that one does not work. Let's try again. Remainder theorem. Plug in -1. Okay, plugging -1 into my polynomial function, and -1 to the 4th power is a +1. All right, minus -1 to the 3rd is a -1. And then -1 squared would be a 1. A -3 times a -1, and then a -6. Okay, so then when I look at this, I add up all my positives. That's 1, 2, 3, 6 minus 6. What do you know? I got a 0. Okay, so what that means to me then is that -1 is going to be one of my zeros because it doesn't have a remainder. Okay, let's keep going. F of, let's put in 2. Right, so 2 to the 4th minus 2 to the 8th plus 2 squared minus 6. All right, so on this one, again, I'm just looking at, here's 16 and 4. Those are my positives, so that's a +20. I got a -8 and a -6. That's a -14. A -6, that's -20. Okay, got a +20, -20. All right, that ends up being 0. I don't want to spend forever typing stuff into my calculator, and mental math is always good for you. So try using your brain a little bit to figure out these out. Okay, so I found another 0. Now remember the fundamental theorem of algebra says I'm supposed to find 4 of them. I just found 2 of them doing the remainder theorem. Let's go ahead and bail on the remainder theorem for right now, and let's look at what we can do with those numbers. Remember that if you know that it's a 0, well, even if it's not a 0, we can run it through synthetic division. I might mention you're going to want to write really little on your notes. I didn't give you much space to work, and some of these take a little bit of space. So -1, and I'm going to run it through the polynomial, the original polynomial, so back up there with a 1, -1, 1, -3, -6. Run it through my synthetic division. And there is that remainder 0 that I knew I was supposed to get. But remember what we did the other day, like right now, since this is a 4th degree polynomial right here, when I run it through synthetic division, what I'm going to have left for this is now a cubic. And I'm trying to get it to be a quadratic so I can factor it. So what I do is I just keep on going. I have another 0 to check. Plug 2 in. So 1, 2. Okay, remember that was the remainder, so I don't use that. And here my new remainder is 0, so that's good. And so what I have left, that was a cubic, so my final result down here is going to be a quadratic. So this 1 is really a 1x squared plus a 0x plus a 3. All right, so really I'd probably call that x squared plus 3. And that's a quadratic, and typically we would factor that. All right, that's kind of a weird one because I ended up with a 0x, so it doesn't really factor. So really I'm just going to set it equal to 0. So let me come over here where I have some more space. Now let's do this. Okay. So I'm going to take my x squared plus 3 and set it equal to 0. Subtract the 3. Square root both sides. Don't forget your plus or minus when you do that. So it's a plus or minus. Ooh, we got that negative in the radical. That's why we did yesterday. That's the whole reason we spent that whole day doing complex numbers, because they're going to start popping up in stuff we do. So what this ends up being is a √3i. All right, so it's still a 0. It just doesn't look very nice. And so what I have, it's the directions said to find the rational zeros. So the rational zeros are really going to be -1, and 2. But since I went to all the work of finding these other zeros, I'm still going to list them. So I also have a plus or minus √3i. So that's 1, 2, 3, 4 zeros. And just looking at that, it doesn't look very pretty, but that's okay. Let's go to that next slide. And let's talk about what we just figured out here. So when we look at it, it says what kind of zeros will x squared plus 3 produce? Well, we already figured it out. They're going to be imaginary. And it takes us clear back to our big packet of what's going on graphically with this. And so tying it back to what we've previously done, okay, when we were graphing, I have two nice, pretty zeros. There's one at -1, and it's only there once, so it's a cut. I have another one at 2, so it's a cut. And then I have these two imaginary zeros. Okay, it's going to behave like a y equals x to the 4th, because that was the highest degree on it. A quartic, so it's going to start high, come down, do some stuff, and go high again. So here's the deal. I'm going to come here, I'm going to cut, and then remember that when you have imaginary roots, that you have to do some little dip-de-doo in your graph. And so that's what's going on right there. I'm going to have the two real zeros, and then since I have two imaginaries, I put a little dip in my graph. All right, so we're not focusing so much on the graph. I just like it to make sense in your head what's going on when that happens. And so we'll really work on just finding what those zeros are. All right, so let's try it again. On this example, let's start off with our fundamental theorem of algebra. Fundamental theorem of algebra says whatever degree it is how many zeros I should find. So this one is a 3rd degree, so I should expect to find 3 zeros. The rational zero theorem says that you take your factors of your constant, which are 1 and 3, over factors of your leading coefficient, 1 and 2. So not a lot there, but now we have kind of a different, we have a 2 in the denominator, so that works out a little bit differently. And don't forget that these can all be positives or negatives, either one works. Now, I have this set up just kind of to be condensed, but what this really means is it could be a 1 over 1, so you could have a 0 of 1. It could be 3 over 1. It could be 1 over 2. It could be 3 over 2. So that's 4 different options plus all the negatives. So there's 8 options again that I have to check. I only need 3. All right, so here we go. We start off and we do our remainder theorem to see which ones will get us a remainder of 0. So I'm going to start off with 1 and plug 1 into the function. And so 1 cubed times the 2 plus 1 squared times 3. And then minus 8 and plus 3. And we figure out what the remainder is going to be, and I think I'm in luck here. That's going to be a positive 8 and a negative 8. That's going to get a 0. So I've already found one, so I know that 1 is going to be one of my zeros. Now last time we did this, I sat there and I went through the remainder theorem a couple times, or really numerous times, but I did it until I got 2 of them to get me a remainder of 0. Let's talk about how many times do you really have to do the remainder theorem. It really goes back to the fundamental theorem of algebra that says I'm looking for 3, right? And that's because this is a cubic right here. Now that we know once you find something that works, what we're eventually going to be doing is running it through synthetic division. And remember that you want to do synthetic division until you can get it down to a quadratic that's factorable. On our last example, it was a 4th degree. So I needed to get 2 of these numbers to run through synthetic division so that it would end up a quartic. In this case, it's only a cubic. So if I have 1 0 and I run it through synthetic division, I'll be down to a quadratic. So I'm pretty much done with the remainder theorem. I'm bailing. Let's go. Let's go run this 1 through synthetic division. Okay, I knew that that was supposed to happen. That's my remainder, so that's gone. It was a cubic, so now I know that this is a quadratic. It's a 2x squared plus 5x minus a 3. It's a quadratic, so it's something I would look to factor. Now, not everything will factor for us, but if it will, we sure want to do that. So 2x and x, my signs are going to be different. I'm going to want a 3 and a 1. That'll get me a positive 6x for my outer, negative 1x for my inner. That's what I want right there. Okay, so we were able to find the other two. So, looking at the directions again say find the rational zeros. Well, I'm in luck here because all of these came out rational this time. There were no imaginaries that I had to deal with. The zeros are going to be a 1, and then I also end up with a 1/2 and a negative 3. And so there's all of my rational zeros. You might take a look over at your rational root theorem and look at the 3 that we came up with. All would come out of this list. And so that's just confirmation that I feel good that our numbers are correct. All right, now it's your turn. All right, now it really is important that you stop the video and you try to do these on your own. Just watching me do 3 or 4 of these will not prepare you to do them yourself. You got to kind of practice doing the steps and knowing what comes next and where do I go from here. Now on this one, I'm going to baby step you through it though. Let's do a little bit and then we'll pause. We'll do a little bit and we'll pause. We'll do a little bit. So right now, I want you to pause. Well, before you pause, let me give you what directions, how far we'll go. Let's just fill in the box, the fundamental theorem of algebra and rational root theorem. Can you do that by yourself? Okay, so pause the video, fill it in, and then in your notes, and then restart it, and we'll see if we're okay. Okay, so your fundamental theorem of algebra tells you that you should have 3 zeros because it is a degree 3 polynomial. Your rational zero theorem says that you should have factors of the constant, and remember it's always a plus or minus. So 12, we have lots of options here. 1, 2, 3, 4, 6, and 12. Okay, a lot of options. All over factors of 10. 1, 2, 5, and 10. Holy cow, lots and lots of options to check on this one. But let's think about this for a second. How many are we really going to be checking in our remainder theorem? Since it's a cubic, how many do you have to find before you can run it through synthetic division and get it to a quadratic? You should be saying in your head, oh, I just have to do it once. Just find one of them, and that'll get me down to the quadratic. Okay, so let's pause the video for a minute, and you go ahead and run it through remainder theorem a few times, find some different ones. All you got to do is find one that works. When you find one that works, then restart. All right, so as you ran it through, it takes a little bit to find the one that works, but you should have had f of 2 that worked. And so f of 2, when you plug that in, you should have gotten a 0. Of course, you have a whole bunch of work shown there of you trying to figure out which one works, but 2 works, so let's run 2 through the synthetic division. Oh, I should have you do this. Okay, you run 2 through the synthetic division. So pause the video, run it through synthetic division. All right, so this is what you should have after you run it through synthetic division. You end up with a quadratic, which is what we want, and so then we're ready to factor this thing. And this one's a little bit weird because your leading coefficient is a negative 10. And just for the sake of time, I'm going to save you on this since maybe you weren't in class and you're watching this because you missed class, but this actually is not going to factor for us. We could sit there and try for a while. I did. I tried to factor it. I couldn't make it factor. So remember from yesterday, if something isn't going to factor, we have another alternative. We're going to run it through the quadratic formula. So let's go through the quadratic formula with this one. So you're going to have x equals negative b, so that'd be a positive 5, plus or minus the square root of b squared minus 4ac. All right, all over 2a. Now, let's clean up that radical mess. So we have x equals 5 plus or minus. Since it's a negative and another negative right here and right here, we end up adding that. So you have a 25 plus 240. So 25 plus 240 is going to be a 265. I was happy at least it was positive. Okay, and that's all over negative 20. And I really don't think that 265 breaks down for us. I wish it had. I cannot reduce the 5 and 20 because the root 265 is also being divided by the 20. So only if you can reduce both of them do you do that. And so I'm pretty much done. I'm leaving it like that. And so the final answer, find the rational zeros. Okay, well, to be honest, 2 was my only rational. But hey, come on, don't just leave it at 2. We did all this other work. So we're going to write 5 plus or minus root 265 all over negative 20. Now that is, because of the plus or minus, is 2 separate zeros. So there's my grand total of 3 zeros. Notice because of the radical that this second one, or the plus or minus, the quadratic formula one, is not rational. And that's why you would not have ever come up with it from your rational zero theorem. This is only going to find the rationals for you, which we got as a 2, which was, yes, one of our options there. Okay, last one. This one we did as a team effort in class because it's kind of a doozy. It's an x to the 5th, so that's a little bit tougher. I'm probably going to walk you a little bit through this and have you do a little bit on your own. So let's start off. Can you fill in the fundamental theorem of algebra and the rational zero theorem? So pause the video, fill those in, then turn the video back on. This is what you should have ended up with. We've got to find 5 zeros, and we really have 8 options here, 1, 2, 4, or an 8, or negatives of those. Okay, so the next thing we need to do is run it through the remainder theorem, and think about this for a minute. You right now have a 5th degree. You've got to work it until you can get it down to a quadratic. How many zeros do you think you need to find doing the remainder theorem? You should say 3. We need 3 of them to find it. Okay, so here's what I'm going to do. I want you to practice doing the remainder theorem. Find at least 1, and then come back to me. Go ahead and pause. All right, I was way too nice there because 1 happened to work, and so you probably found that one and just went ahead and jumped in. Okay, so negative 2 is another one that happens to work there. But remember that we have to have 3 of them. So what we're going to do is kind of cheat a little bit on this one. We did it as a group in class, and so we talked about this and we kind of split up the work. You might be working forever on this one. So let's look at what happens on this. I'm going to cheat a little bit and look at the graph of it. All right, so here's a picture of that graph, and it's just a really zoomed in shot of what I want you to see on this. But if you look at this, the zeros on this, you can see that there is a 0 sitting at negative 2 right here, and you have a 0 also at 1 right here. But what I want you to notice is, what is it doing at 1? Think back to our packet. It's actually bouncing at 1. And there's only one way to make it bounce, and if that 0 has a multiplicity of 2 or 4 or 6 or some even power. So when I went and found my zeros and I found 1 to work, it actually is a 0 multiple times. So if you can tell by this graph, I really only have these 2 that I'm ever going to find on my remainder theorem. So I'm going to again, bail on the remainder theorem. Now that I've found what I needed, go to synthetic division. So here we go. I'm going to plug 1 into synthetic division. And so you got a 1. Notice the 0 for x to the 4th, 1 for x to the 3rd, 2 for the x squared, but then there's not an, oh yes there is, sorry. There is a x term, and then there's your constant. Okay, so we're going to run that through, 1, 1, 1. Okay, there's my 0 remainder. Okay, now here's the deal. Remember that it bounced at 1? So 1 is going to work again when I run it through my synthetic division because it has a multiplicity of 2. There it is. There's my remainder. Okay, so now let's see. I started at an x to the 5th. So then it was an x to the 4th at this stage. This is an x cubed. I got to keep going. Got to get it to an x squared. So now I'm going to go back to that negative 2 that I found and run it through. Okay, there's that remainder. All right, so now I'm down to a quadratic. So that is the equivalent of an x squared plus 4, which again is not one of the normal ones that we would typically try to factor. And so what that gets us is an x squared plus 4 set equal to 0. Subtract the 4. Square root both sides. Don't forget your plus or minus when you square root both sides. The square root of 4 is just a 2, but since it's a negative 4, it's going to be a 2i. All right, so here's what we've got. We were supposed to have 5 zeros. I have 1, 2, 3, 4, 5. I've got them all. So now let's look at what the directions were actually asking us for. It says find the zeros. Okay. Write the linear factors or the irreducible quadratic. Okay, so here we go. Here are our zeros. Let's just list those out. We'd have a 1. There's not really any reason to write it twice. It just touches the x-axis at 1. Don't write it twice. And negative 2. And plus or minus 2i. Those are the zeros. Now the factorization, or the linear factors, looks like this. I'm going to have to squeeze this in here. Actually, I'm going to come down here where I have just a hair more room. So, all right, so we're going to have an f of x. Oops, let me get my pen here. F of x equals, the first 0 we had was an x minus 1. But remember that that bounced there. We ran it through synthetic division twice, so our x minus 1 actually needs to have a squared on it. Okay, the next one was a negative 2, but that was only there once. And then we have this plus or minus 2i. Now normally when we write factors, we don't have imaginary numbers in them. So that's what this or irreducible quadratic means. Irreducible quadratic means, well, typically, when we get down to this stage of a quadratic, we like to factor that and get some nice factors. We weren't able to do that, so what they're asking us to do is go ahead and leave the quadratic there as opposed to writing ugly linear factors. And so I'm going to finish this up then and just leave it as an x squared plus 4. And then that's going to be my factorization. You can tell that there's a 2, 3, and then this is a quadratic 4, 5, so this is a 5th degree polynomial. I have all my factors there. All right, so we've done several examples. We're kind of done doing that. Go back and watch them again if you're still not sure on something. Let's talk about a few things, though, that I want you to recognize what we've kind of come across here. One of the things to notice is that when you have complex zeros, those are your imaginaries, anytime that that happens, you're going to find that those always come in conjugate pairs. All right, so if you got to think about where they are coming from. They're coming from something like an x squared plus 4 equals 0, and then you subtract it and you square root it, and you end up with this plus or minus because you had to square root both sides. And so when you square root like that, That was actually a negative 4. Okay, so this plus or minus right here is what is making these come in conjugate pairs. Okay. The other place that you could get imaginaries is through the quadratic formula. But remember, on the quadratic formula, x equals negative b. Oh, here again is your plus or minus the square root. So when you do your quadratic formula, sometimes you're going to end up with a negative number under here, but it's still going to have this plus or minus on it. So that's still going to make it come as a conjugate pair. So keep in mind, anytime you have complex zeros, you don't have 1, you'll always have 2 or 4 or 6. It always has to come in pairs. Okay, so let's use that idea to do something here. It says, find a 4th degree polynomial that has 1, negative 1, and 3i as zeros. All right, so a 4th degree polynomial, so f of x equals, it has 1 as a 0. So that tells me it's going to have x minus 1 as a factor. It has a negative 1, so that's an x plus 1 as a factor. It has a 3i, so that's x minus 3i. But that's only a cubic. That's a 3rd degree, because there's only 3 of them. So sometimes you have to use your head a little bit and say, oh wait, 3i was a factor. That must mean that negative 3i was also a factor, because they come in conjugate pairs. So if negative 3i was a factor, or was a 0, then I'd have x plus 3i as my last factor. Now it's a 4th degree polynomial. I do want you to clean that up and make that look like a nice polynomial that I would give you. So let's do FOIL on these first two. So we'll have an x squared. Now notice those are conjugates, so your plus x minus x drop out, and you just get a minus 1. I'm sorry, that first one was an x squared. Okay, so you get x squared minus 1. Let's do it again on these last two terms. First gets you x squared. But again, outer is a 3ix, inner is a negative 3ix. Those are going to drop. So last gets me a negative 9i squared. But remember from yesterday that I squared is really just a negative 1. So what I'm going to do is just change that to a plus 9, and I'm going to get rid of the I squared then. All right, one more time. Let's FOIL that mess together. So x squared times x squared plus so we have a 9x squared for outer minus 1x squared for inner. So that's an 8x squared. And then minus 9 for the last. And that is our 4th degree polynomial that would have all of those as zeros. Okay, we have done some amazing stuff here, and I am whooped. Why don't you take a break, go get some cookies and milk, get me some while you're at it, take a break. Let's finish them out here after you have taken a rest. All right, I knew you couldn't stay away. Here we go. Let's finish this out. We're not going to be finding the zeros anymore. Actually, it'd probably be smart. I should have told you, go practice doing. Go get started on your assignment. Practice doing it a little bit first. So maybe you want to pause now and go do that. That'd be all right. Otherwise, really what we're finishing up is we're just looking at some of those different situations that have happened and some different theorems that we can look at that help us understand kind of what's going on, some different features in these polynomials. So here's one, Descartes' rule of signs. Okay, René Descartes, he was a mathematician, French mathematician, and he did a lot for the math world. This is just one of the things he has come up with. So his rule of signs says, and this is a nice textbooky definition, good for us to kind of figure out what they're talking about. The number of positive real zeros of a polynomial function is equal to the number of sign changes in f of x, or less than that by an even number. Okay, so what that means is we're going to look at the function and we're going to see how many times that sign changes. and that's going to tell us how many positive zeros there are. Okay, the number of negative real zeros of your function is going to be equal to the number of sign changes in f of negative x, or less than that by an even number. Okay, so let's look at what this means. So we're going to go back to our team effort problem. So flip back in your notes to that team effort problem, and let's look at what that was. All right, so here's the function that we had, and all you're doing is you're looking at this function left to right, and you're just counting up how many times your sign flips back and forth from positive to negative. So if you look at this, the first term is a positive term. The next term is also positive, so it didn't change. The next term is also positive. Oh, right here, look how it switched. Now it's a negative 12. So right here, we had a sign change go on. Oh, and then it went back to positive. So there's another sign change going on. So we saw two sign changes. So the number of positive real zeros is equal to the number of sign changes. So that tells me that I should have two positive zeros. And if you look back at that problem, on our team effort problem, we had one, and then, but remember that it was there twice, and so it would actually be counted as two positive zeros. Okay, good. Let's look at the second part of this. Now what we're going to be doing is finding f of negative x. So we have to put a negative x in for all of our x's. I think I'm going to leave that there, and I'm just going to squeeze it in up here. And so for f of negative x, that just means put in a negative x. So a negative x to the fifth is going to be a negative x to the fifth. Put in a negative x to the third, that's going to be a negative x to the third. But on our next one, since we're squaring it, that's going to go back positive. So that'll stay a positive 2x squared. And if I take a negative 12 times a negative x, that'll go to positive 12, and then the 8's not going to change. Okay, so now let's go through and see how many times the sign changed. So it was negative, still negative, went positive. Okay, right there a sign changed. So that's one, but then it stayed positive and it stayed positive. So there's only going to be one negative, because remember the number of negative zeros is equal to the number of sign changes in f of negative x. So I only got one sign change. If you look at this, back at this problem, we got a negative 2 for one of our real zeros. Notice they are talking real zeros. I had a negative 2, so there's my one real zero. Okay, let's talk a little bit about what this means. Okay, let's do another problem. And we'll generally set up kind of a little chart of what the possibilities are. So here's my new function. All right, so determine the possible positive and negative zeros. So the positive zeros, I just go left to right here and see how many times the sign changed. It was positive, now it's negative, so that's 1. Now it switched to positive. Here, let me just actually write that in. So we went to there, so it switched to a negative, switched back to a positive, so there's another one, stayed positive, went to a negative. Okay, so I have 3 positive or possible positive roots. Okay, then you come back and you got to do f of negative x. Okay, so that just means you're plugging in a negative x for all the x's. So if you plug it in for an even power, it's not going to change it because that negative will go away. But if you plug it into an odd power, it's going to affect it. So a negative x to the 4th is still an x to the 4th. A negative x cubed is going to be a negative times the negative 3 is going to make it a positive 3x cubed. Plug negative x in and square it, that's going to be positive, so that won't change this one. Plug the negative x in down here, it will be a negative 2x, and then a negative 60. All right, so here we go. Left to right, we're counting how many sign changes we see. Starts off positive, still positive, still positive. Oh, right there, it switched to negative, so there's one, but then it stayed negative. So there's only going to be one possible negative 0. All right, so that's what we did last time. Now let's finish out the rest of this. It says, or less than that by an even number. What that means is you could go down by 2's. So right here where I have 3 positive zeros, I could be less than that by an even number. So I could go down by 2 or 4 or 6. Well, it's not big enough to go down by that much, but it could go down by 2. And so I might only have 1 positive and 1 negative. But remember, I should come back and I should have finished this out. We could have 3, 1, that means no imaginary, which gives us a grand total of 4. And since this is a quartic, I would expect to have a grand total of 4 every time. But in this case, it might be 1 positive, 1 negative, which means that there are 2 imaginary. So then that adds up to 4 total. Now these are my 2 options. One of these things could happen. We're not going to do this problem, but I know going in then that I should end up with 3 positive and 1 negative, and they're all real, or maybe 1 positive, 1 negative, and I'll end up with a couple imaginaries when it's all said and done. Now, this should kind of make sense to us why we are decreasing this number by 2, or less than that by an even number. It goes back to what we said earlier. Remember that these imaginaries always come in pairs? So I couldn't have like 1 there or 3 there. They have to come in pairs. Maybe don't have any at all, or I've got to have 2. Right? This was not a very high power. It was only a quartic, so I'm not going to have a whole lot of options there. As I start to have higher degrees, then I can have a lot more going on in my sign chart. Okay, let's try one more. Now why don't you try this one on your own, go through and see the sign changes for the positive, and then let's check it. So pause the video, go do the work. Okay, that wasn't too hard, was it? Everything was positive. I don't have any positive zeros. So now what I want you to do is to go find f of negative x, and then see how many sign changes you have. Pause the video, go do the work. Okay, this one had a lot of sign changes in it. You should have ended up with a 3 for your negative. Now, that's actually kind of helpful. If we do this, and we may not get around to the point where we get to have a day where we kind of throw all that together, but ideally what you're doing is you're doing this Descartes Rule of signs, like after you do your rational zero theorem. Because here's the deal, something like this, I don't even have any positive roots. So I wouldn't even be trying in my remainder theorem, I wouldn't even be trying the positive. It kind of eliminates a lot of possibilities. I'm jumping in, doing negatives, 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 because that's all there are going to be. Okay, so let's finish up our chart though. This says there are going to be 3 zeros. So the way I have it set up right now, I have 0 positive, 3 negative. I don't know why this doesn't say imaginary right here. But then I would have 0 imaginary, which gets me a total of 3 complex. But remember, it can be that number or less than that by an even number. Okay, so that means go down by 2's. Well, 0 can't go down any farther, so it's going to stay a 0. But this 3 could go down by 2, so maybe there's only 1 negative, which would leave us with 2 imaginaries, so I have a grand total of 3 zeros. So either of these scenarios could be working. Okay, so that's kind of the idea. I want you to try one more. Actually, now, let's call that good. You can go back and watch a few of these if you need to. But this is just kind of one of those ways to kind of identify what your zeros should be looking like. All right, we have one other thing to try, and that's the upper and lower bound. All right, again, kind of a nice thing to evaluate what it is that's going on with our function. So f of x is divided by x minus c using synthetic division. Okay, we've been doing a bunch of that. We've been doing synthetic division left and right. Now, if your c that you're plugging in, it's kind of like our k, really. So if k is greater than 0, so it's going to be a positive number, and each coefficient in the resulting division is positive. Okay, let's kind of write that out, what they're talking about. Remember, you're just doing your synthetic division. You got some C value up here, you got some numbers here, and you're going to do this business. And what it's saying is that if your C is positive, and each coefficient in the resulting division, so you're talking about all of these numbers down here, if each one of those is positive, or it can be 0, then C is an upper bound, and there are no real zeros greater than that, meaning nothing is ever going to get bigger than that. Okay, so again, if I was doing my remainder theorem and I figured out that 4 was the biggest one, I'm sure not going to be putting in 8 or 16 or anything like that. Okay, let's look at the second part of this. If C is less than 0, okay, so now you're putting in a negative number right here, and each coefficient in the resulting division, that's this, alternates positive and negative. So it goes plus, minus, plus, minus, plus, minus, or 0. Zeros are kind of like wild cards. They can count as positives or negatives. Then C is going to be a lower bound, and there are no zeros smaller or less than C. Okay, so if that's a negative, it kind of gives me a boundary of to know, do I keep trying numbers smaller, or do I keep trying numbers bigger, or not? Okay, one of the places that we really like to is in when you're looking at a screen on your calculator. So we've played around with this function and finally got a window that we can see what's going on, but it's not an ideal window if you look at kind of what it's scaled by. So what we can do is use our upper bound and lower bound to see if we're missing any important stuff. So it says, assume the given graph is what Joey is looking at on his calculator. Use the upper and lower bound theorems to determine if there are any zeros beyond his screen that he is missing. Okay, so this is what we're going to do. Now the C value that you pick really is your choice, but you don't want it to actually be a 0. You can't put a 0 in and run it through. So when I'm looking at my screen here that he's looking at, I would probably go with a -2. This is going up a ways, and what I'm wondering is it possible, is this thing like going up and then it's eventually going to come down or something, and am I missing something out here? Or is this it and it's just going off to infinity? What's the deal? And so I would put 2 probably as my upper bound, and I'm wondering, is there anything bigger than 2 that I'm missing? So let's put 2 as our C value. And then you put in your coefficients from your polynomial over here. Here's your polynomial. So put in your coefficients, and notice that there's not an x to the 4th, so put a 0 there, and then a -1, and a 7, and then we don't have an x term, so put a 0. Oops, I don't really need those pluses in there. All right, so we got 1, 2, 2, 4, 3, 6, 13, 26, 52. Okay, now I didn't get a remainder 0. I wasn't expecting to, because I know from my graph 2 is not one of my zeros. It's not touching at 2. So really what I'm looking at is this right here. I'm looking for all of those. Remember that if this is a positive number, then I want these to all be positive. And they are. So what that tells me is that 2 is an upper bound, so that's what we write. 2 is an upper bound. And I don't have any zeros bigger than that I'm missing. Or Joey doesn't, I guess, in this case. And maybe a note to yourself, all positive coefficients. That's sloppy, sorry. Okay, let's try it again. But this time I'm checking on the left side of my graph. So I'm wondering over here, I see that it crosses close here at -2. And we can't put that in, but let's put in a -3. I'm wondering, is it going to turn back around and come back up and cross? So let's check it. All right, I'm going to have to write really little here. Change my font size here. All right, so I'm going to put in a -3 because that's the edge of my graph. put in my coefficients. Okay, so again, it didn't end up with a zero remainder, wasn't expecting it to. What I'm checking here, and remember when you look back at what your theorem says, that if this value here is negative, then you are looking for these coefficients to alternate. What do you think? Do they alternate signs? They sure do. Okay, so what that means is that -3 is a lower bound. So Joey is not missing anything from his calculator. He's got it all. And let's make a note here, alternating signs is what we're looking for. Now that wasn't very interesting. Unfortunately, I was maybe hoping something would turn around and I'd miss it. And so what would happen there is that your signs wouldn't alternate. Or on this first one, you might get a negative thrown in there someplace. So that's what you're looking to have happen. Okay, let's try one last one. Okay, this is our last example. Can you believe it? We finally hit the end of our notes. So what I want you to do is try this one on your own. You check, rather than them giving me like a graph screen that I pick my upper and lower bound, they've given me options for my upper and lower bound. So they want to know, is 4 the upper bound? So run that through synthetic division. And then is -1 a lower bound? So run that through synthetic division. And then make a statement on what you think. Yes, it's an upper. No, it's not an upper. What do you got going on? Okay, and one hint before you get started, notice that you are missing some terms in this polynomial, so don't forget to put your zeros in there. All right, so pause the video, do the work. Bet you didn't expect that, huh? They both worked again. I'm just throwing a loop at you. It won't always work out that way, but on this first one I wanted you to notice, look at all those zeros that happen. Remember, those are wild cards, so all I'm really looking at is the 1 and the 15. So those are both positive. 4 is an upper bound. My -1, they alternated beautifully, so that's a lower bound. Okay, so you just got to check it. This is kind of your work, so don't just write yes or no. I need to see this right here. That's what verifying means. Verify means show me, prove it to me. And so your work is that proof. Okay. This has been fun, hasn't it? All right. Well, good luck. Go get to work on your homework.